Hi, hello students. Good evening, everyone. Okay, I hope all are doing well. Anyway, warm welcome all of you to the YouTube channel of Infinity Learn by Sri Chaitanya. This is me Surya, your chemistry faculty from Infinity Learn. Okay, today we are going to the last part of our session, that is the chemical bonding and molecular structure. We will be starting with the session we have taken last classes, that is about the hybridization. Before that, there is a gentle reminder about the AITS. Okay, you will get a coupon code of YouTube 50 off, then you will get the discount of 2999 for the all India test series for JEE Session 2 and JEE Advanced. Okay, quickly let us start our session, that is the main part, hybridization. After completing the hybridization part, we will be moving to the next important topic, that is the molecular orbital theory. Okay, the first one, the hybridization. I will be discussing about the hybridization of some of the organic molecules. The first one, it is ethane molecule. Okay, ethane molecule. Yes, you can see here, this is a complete hybridization of ethane molecule. Before that, you have to identify the steric number of molecule, right? Steric number in order to predict the hybridization. As we all know, ethane molecule is CH3, right? Okay, this is our molecule CH3. So first we have to predict the steric number of each of the carbon atom present in the ethane molecule. So I can say that here completely 3 hydrogen plus 1 carbon, right? Completely 4 sigma bonds are forming. So I can say that the steric number of this particular carbon atom is 4, right? There is no any lone pair, so I am taking here 4 plus 0, that is equal to 4, which means that it belongs to which hybridization? If the steric number is 4, it will belongs to which hybridization? sp3, right? 4 means sp3 hybridization. So I can predict that in the case of CH3 molecule, this carbon exhibit sp3 hybridization as well as this carbon is also exhibiting sp3 hybridization, right? So I want to draw the structure of the ethane molecule by using the hybridization. So here you can see that sp3 hybridization, right? This will be the structure of carbon. Before that, you have to identify the configuration of carbon, right? Electronic configuration of carbon in the ground state. So I will written it as 1s2, 2s2, 2p2, right? Now during the excitation, this one of the electron will go to the third orbital in order to form the sp3 hybridization. So I will written it as right, this will be the excited state electronic configuration of carbon. So these 4 orbitals will undergo hybridization to form 4 sp3 hybridized orbital, right? 4 sp3 hybridized orbital. Then what will happen here? After entering these 3 hydrogen atom, it will overlap with the sp3 hybridized orbital of carbon, right? So whenever 3 hydrogen atoms are arising here, we can say that electron will fill up here. In these 3 orbitals, hydrogen atom will overlap, and from here one of the carbon atom will always overlap, right? So it will form the structure like this. Okay, this will be the sp3 hybridized orbital of carbon atom. 1, 2, 3, 4 sp3 hybridized orbital, right? Similarly, for the next carbon atom is also, it is containing 4 sp3 hybridized orbital. Then you can see that these 3 orbitals, right? These are the 1s orbital of hydrogen atom. It will overlap with each other, right? So it will form the sp3s sigma bond, right? sp3s sigma bond. What about here? Again, this is also sp3s sigma bond. Here also sp3s sigma bond, right? Similarly, in total 6 sp3s sigma bond is formed here, right? Because it is the axial bond is forming here, axial overlapping. In total 6 sigma bonds are forming sp3s sigma bond. Then what about here? Here 2 sp3 hybridized orbital, right? One of the sp3 hybridized orbital of one carbon atom which overlap with the another sp3 hybridized orbital of another carbon atom. So it will form sp3 sigma bond, right? So this will represent the structure of CH3 molecule. Clear? Okay, Prashant, steric number is the number which is used to predict the hybridization. According to the number of sigma bonds and lone pairs, we can predict this number, right? So I can say that steric number is equal to the total number of sigma bonds, right? Total number of sigma bonds plus number of lone pairs present on it. Number of lone pairs present on it. Right? That will be the number. Depending upon the number, we can predict the hybridization. If it is 2, it will be sp hybridization. Then if it is 3, it is sp2. If it is 4, sp3. 5, sp3d. 6, sp3d2. Right? This will be the prediction of steric number. You can just go through my previous session, which is already recorded there. I had discussed about the steric number and hybridization detailing. Clear? Okay, this is the hybridization about the ethane molecule. Now let us start with the next molecule, that is ethene molecule. And also you can see here the CC bond length is 154 picometer. This is 154 picometer. Then each CH bond length is 109 picometer. Clear? Now here is the next molecule, that is the ethene molecule. Okay, here you can see the structure of the hybridization of the ethene molecule. As you can see here, this will be the structure. So we can predict the steric number here. What about the steric number of this carbon atom? How many sigma bonds are forming there? In the case of first carbon atom. This is one sigma bond, this is one sigma bond, this third one, right? So 3 is the number of steric number here. So we can say that carbon atom is having the sp2 hybridization. Similarly for this carbon atom, also it is sp2 hybridization. So we can draw the hybridization here. Before that, we have to write the ground state electronic configuration of carbon. This will be the ground state, right? During excitation, it will goes to right? This will be the excited state electronic configuration of carbon atom. So we can say that these 4 orbitals will form 4 sp3 hybridized. Okay, our hybridization is sp2, right? So we can say that here this is a particular condition in which these 3 orbitals, 1s and 2p orbital, will undergo sp2 hybridization. sp2 hybridization. Then what will happen to this one? This will remain unhybridized, right? This will remain unhybridized. Okay. Now, whenever the hydrogen atom is entering here, these, right? Here, 2 hydrogen atom is present, right? 2 hydrogen atom is present. So, 2 electrons from the hydrogen atom is overlapping here. Here, one of the carbon atom get overlapping, right? So in total here sp2s overlapping is happening. sp2s sigma overlapping is happening, right? sp2s sigma bond is forming here. Clear? So we can say that this is the sp2 hybridization, right? sp2 hybridized structure is here. So here this is the 1s orbital of hydrogen. This will overlap with sp2 hybridized orbital of carbon to form 2 sigma bonds here and 2 sigma bonds here. So in total 1, 2, 3, 4 sigma bonds, right? 4 sigma bonds are formed by the overlapping of sp2 and s orbital of the hydrogen atom. Then what about this one? This is our unhybridized 2p-z orbital, right? This is a 2p-z, this is 2py, and this is a 2px, right? So this will be our unhybridized 2p-z orbital. So these unhybridized 2p-z orbital always overlap with the sidewise overlap, right? This will be the sidewise overlapping, resulting in the formation of pi bond. Right? Pi bond. So we can say that in the case of CH2 molecule, one pi bond is arising due to the overlapping of unhybridized 2p-z orbital of carbon, right? Unhybridized 2p-z orbital of carbon. So this will be the sp2 sigma overlapping, right? Okay. This will be the complete hybridization of ethene molecule. Then this will be the structure, right? Clear? Bond angle will be 120 degree. Clear? Again, bond length is given here, it is 1.34 angstrom. There is Cc bond length. Then sp2s sigma bond length is 108 picometer, right? The last case, it is the ethylene molecule, right? Sorry, acetylene molecule, which means molecule containing triple bond, right? So CH triple bond, CH is the chemical formula of acetylene. Otherwise, it is also known as ethyne molecule, right? Ethyne molecule. Okay, while calculating the steric number, you will get that in total 2 sigma bonds, right? Total 2 sigma bonds. So steric number is equal to 2, or hybridization is sp hybridization. So this carbon is sp hybridized. Similarly, this carbon is also sp hybridized. Now we have to write the electronic configuration, right? Excited state electronic configuration. Okay, these two orbitals, this is 2s, right? 2s, 2px, 2py and 2pz. These two orbitals will undergo sp hybridization. sp hybridized orbital. It will form sp hybridized orbital. Then two hydrogen atom, right? Okay, 2 hydrogen atom from one of the hydrogen atom is overlapping here. Okay, overlapping here, and this carbon atom. This electron is coming from the neighboring carbon atom. Completely, it will form sp-s sigma bonding, right? sp-s sigma bonding. This is for one carbon atom. Similarly, for the next carbon atom also, same hybridization and overlapping is happen. So we can say that in the structure of sp molecule, right? The structure of sp molecule, this will be our sp hybridized orbital, right? The center one. Okay, this will be the sp hybridized orbital, right? First one, this sp hybridized orbital will overlap to form sigma bond, which will represent the first sigma bond here. Then what about here? It will overlap with the 1s of hydrogen atom to form sp-s sigma bond. Similarly, here is also sp-s sigma bond is forming by the overlapping of 1s orbital of hydrogen atom. So this is representing the CH sigma bond and CH sigma bond. Then what about these orbitals 2px and 2py? They remain unhybridized, right? They remain unhybridized. So we can say that these unhybridized orbitals always undergo sidewise overlapping, right? Sidewise overlapping. So, as you can see here, this is our py orbital of carbon, which is remain unhybridized, and also this is the pz orbital, right? This is the pz orbital remain unhybridized. This py orbital will undergo sidewise overlapping to form one of the pi bond. Similarly, pz orbital, right? This pz orbital will undergo sidewise overlap to form another p bond, another pi bond, right? Another pi bond. That will represent the triple bond in the CC triple bond, right? This will represent the one of the sigma bond. Then another two bonds are represented as two pi bonds, right? Clear? Then because of the sp hybridization, it will have the bond angle of 180 degree with linear structure. Clear? Okay, so far we discussed about the hybridization starting from the sp, then sp2, sp3, sp3d, sp3d2 and sp3d3. And these are some of the examples along with their shape. I have already discussed about these things very detailedly in the previous class. You can just pass through it. You can just go through it. Okay. Now in this particular lecture, we are going to discuss the most important theory, that is the molecular orbital theory, right? Okay. Molecular orbital theory was proposed by F. Hunt and R.S. Mulliken. F. Hunt and R.S. Mulliken in 1932. Then, what is the speciality of molecular orbital theory? Any idea? Okay, as the name it suggests that it is based on the molecular orbitals, right? So we can say that whenever we are considering about there are some features. Whenever we are considering about the atoms containing atomic orbitals, right? Similarly, in the case of molecules, these orbitals are termed as molecular orbitals, right? Electrons in a molecule are present in the various molecular orbitals, as the electrons are present in the atomic orbitals in the case of atom, right? This is the first speciality of the molecular orbital theory. A term is introduced as the molecular orbital. Whenever we are considering about the molecular orbital, the electrons are filled in their molecular orbital as that of the atomic orbitals, right? Now, how these atomic orbitals are formed? These atomic orbitals of comparable energies, right? Atomic orbitals of comparable energy or have the similar symmetry, proper symmetry, combine to form molecular orbitals. The next question arising that how these molecular orbitals are forming. The molecular orbitals are forming by the combination of the atomic orbitals having similar energy and similar property. Similar symmetry, right? Similar or proper symmetry. Now, there are some difference between the atomic orbital and molecular orbital, right? As you can see here, I have already highlighted here that atomic orbital is monocentric while molecular orbital is polycentric. What do you mean by that? Monocentric and polycentric. This is based on the nucleus, right? So, in the case of an atomic orbital or an atom, only one nucleus is present, right? If you are considering only one atom, it is influenced by one nucleus, right? So, whenever we are considering the molecular orbital, it will consider about the molecule. It contains more than one atom, right? Which means it contains more than one or two or more than two nucleus are present. So, that is why they are calling as the molecular orbital is polycentric. Clear? Now, whenever the atomic orbitals are combined together to form molecular orbitals, we can say that the number of molecular orbitals formed is equal to the number of atomic orbitals combining, right? So, if example, if I am taking two atomic orbitals, right? So, this will be one atomic orbital represented by AO. Then if I am taking another atomic orbital, 2, right? which means two atomic orbitals are combining. So I can say that two molecular orbitals are forming, right? Two molecular orbitals are forming. So these two molecular orbitals are named as, first one it is bonding molecular orbital, right? Bonding molecular orbital. And it is represented as BMO. Then next one it is anti-bonding molecular orbital. Okay, these are the two types of molecular orbitals which is formed by the combination of two atomic orbitals. So, as you can see here, generally bonding molecular orbital having less energy as compared to anti-bonding molecular orbital, right? It has less energy, or energy is decreasing here. It has more energy. So, the bonding molecular orbital has lower energy and has great stability, right? As the energy decreases, its stability increases, right? So we can say that in the case of bonding molecular orbital, it will be more stable as compared to the anti-bonding molecular orbital, right? Now, whenever these atomic orbitals are combined together to form molecular orbitals, again the electrons are get starting here, right? Electrons are get filled in the molecular orbital according to their principle, right? Aufbau principle. I think you have studied about your structure of atom, right? The second chapter you have studied about the filling of electrons in the atomic orbitals, right? It is based on the three principles: Aufbau principle, Pauli's exclusion principle, and the Hund's rule of maximum multiplicity. Similarly, whenever we are adding electrons to the molecular orbitals also, it is again based on the three rules like Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Clear? Now the question arises that how these atomic orbitals are combining, or how these molecular orbitals are exactly forming, right? So again, in your second chapter, structure of atom, you have studied about the shape of atomic orbitals, right? In the case of that, we can derive that the atomic orbitals are formed by the wave functions, right? By solving the Schrodinger equation, you will get a value of psi, right? This will represent the amplitude of wave, or we can say that the atomic orbitals are represented by the electronic waves, right? So psi represents the amplitude of that wave. So while solving the Schrodinger equation, you will get the answer of psi according to the atomic orbital. But whenever the molecular orbital contains more than one electron, it is very difficult to solve in the psi equation or the Schrodinger wave equation. So we are proposing a new theory or the new concept about the linear combination of atomic orbitals, or it is represented as LCAO. That is the linear combination of atomic orbitals. This is based on the wave mechanics concept. I hope you have studied in your physics chapter about the interference, right? So here in this case of waves or the atomic orbitals, the molecular orbitals are formed by the combination of atomic orbitals based on the concept of interference, right? So for example, if I am taking any wave, right? Okay, for example, these are the two waves I am taking. This will be plus phase, this will be minus, this will be plus, right? So I can represent this wave as a psi A. then this one as a psi b, right? If it is going for the constructive interference, which means that the same phase will reinforce, right? The same phase goes to the same side. So I can say that completely what will happen here, while moving here, these two phases will, this will be the same phase, this will reinforce each other. So it will form a wave like this, in which it have maximum amplitude, right? Maximum amplitude. So what will be the amplitude here? This psi a represents the amplitude of first wave. Right? Psi a represents the amplitude of first wave and psi b represents the amplitude of second wave. Then what will be the resultant wave having the amplitude? Psi a plus psi b, right? Which means these are adding, so I can say that this will be the psi a plus psi b. Psi a plus psi b. So we can say that during the addition of atomic orbitals, constructive interference happens, or we can say that this will result in the formation of our bonding molecular orbital. Right? This will result in the formation of bonding molecular orbital. Clear? Now, what about the anti-bonding molecular orbital? Now I am changing the phase of these waves. So what will happen? While change the phase, it will for the out of phase interference, right? Out of phase interference, or we can call it as destructive interference. Destructive interference. As a result of destructive interference, the amplitude of the resulting wave decreases, right? Amplitude of resulting wave decreases. So we can represent this wave as low amplitude, right? Low amplitude. So if I am taking this amplitude of this wave as psi a, if it is psi b, then what about the resulting wave? What about the amplitude of resulting wave? Psi a minus psi b, right? Which means this will result in the formation of anti-bonding molecular orbital. Anti-bonding molecular orbital, or we can say that whenever two atomic orbitals are going for a subtraction or difference, right, it will form the anti-bonding molecular orbital. Clear? This will be the linear combination of atomic orbitals, which is based on the wave mechanics, that is the basics of constructive and destructive interference. Whenever two atomic orbitals are undergoing for the in phase or the constructive interference, it will form the resulting wave having maximum amplitude, resulting the formation of bonding molecular orbital. Similarly, if it is undergoing the destructive interference, the amplitude of the resulting wave decreases, resulting in the formation of anti-bonding molecular orbital. Clear? This is the representation of molecular orbital diagram. As you can see here, this is the energy part. This is the first wave corresponding to psi a, amplitude of first wave. Then bonding orbital is formed by the addition of the individual atomic orbitals, that is psi a plus psi b. This will be the this will be the anti-bonding molecular orbital, anti-bonding molecular orbital, and this will be the bonding molecular orbital, right? Antibonding molecular orbital. Okay, antibonding molecular orbital is formed by the subtraction of the individual atomic orbitals. So you can see here this is the psi is minus psi b, and also whenever the bonds are forming or the combination are forming by the axial overlapping, it will result in the formation of sigma bond, right? So we can represent the sigma bond as this letter, bonding molecular orbital as sigma here. Then what about the anti-bonding molecular orbital? It will be represented as sigma star, right? Whenever you see star on any of the orbital, it will be representing that it is anti-bonding molecular orbital. Clear? Now, in order to combining the atomic orbital, there are some conditions to be satisfied, right? What are the conditions? Which is already mentioned that whenever two atomic orbitals are combining, it should have the same energy, right? So I can say that whenever I am taking 1s orbital, then it will combine with 1s orbital only, right? Because they have the same energy. It will form the molecular orbital of 1s, right? Then we have already discussed that only the s orbital will always undergo sigma overlapping, right? Or the axial overlapping, resulting in the formation of sigma bond, right? Resulting in the formation of sigma bond. So I can say that this will be the sigma 1s orbital, or again it will form the anti-bonding also, right? So it will represent as sigma star 1s. Star means it is the anti-bonding molecular orbital, right? The main condition is that the combining atomic orbitals always have the same or nearly same energy. Clear? The second point is that whenever these atomic orbitals have the similar energy, there is one more condition. It should satisfy the similar symmetry also, right? Similar symmetry also. For example, if I am taking 2p-z orbital, right? 2p-z orbital, there are 3 2p orbitals, right? There are 3 p orbitals, px, py and pz. Because they are in the same energy level, we assume that we will form combination, right? Because they are at the same energy. But the condition is that if we are taking 2p-z orbital, it will combine with 2p-z orbital only because of their same symmetry, right? If 2p-z orbital of one atom can combine with 2p-z orbital of other atom, but it does not combine with the 2px and 2py because of their different orientation. Clear? Different orientation or different symmetries. The last condition is that the combining atomic orbitals must overlap the maximum extent to get the maximum strength, right? Okay, fine. These are the main conditions to satisfy the linear combination of atomic orbital, resulting in the formation of molecular orbital. Now let me move to the applications of the molecular orbital. So this will be the molecular orbital diagram. As you can see here, this is the first 1s orbital, right? Okay, this will be the 1s orbital. This 1s orbital will form two molecular orbitals, right? One is bonding molecular orbital, that is represented by sigma. Then this one is the anti-bonding molecular orbital, represented by sigma star 1s, right? 1s orbital is always forming the axial overlapping, so it will form sigma 1s and sigma star 1s. This will be the structure of resulting molecular orbital. Clear? Similarly, 2p-z orbital also undergoing the combination to form sigma 2p-z and sigma star 2p-z orbital. The last one, pi 2px and pi 2py. It is formed by the combination or the overlapping of sidewise overlapping. That is why pi bond is forming here. Then bonding is represented by the pi 2px and anti-bonding is represented by the pi star 2px. This is the same image or the same diagram which is shown in your NCERT textbook. Now let us discuss the applications of molecular orbital theorem, that is writing the electronic configuration or molecular orbital electronic configuration of different molecules, right? There will be some order of the atomic orbitals. There will be the order of molecular orbitals. The first one is the sequence of increasing order of energy of various molecular orbitals up to 14 electrons, right? Up to 14 electrons. Okay, these are the resulting molecular orbital formed by the combination of atomic orbital sigma 1s, sigma star 1s, sigma 2s, sigma star 2s and so on. So, if you have the electron number of 14 electrons, you will be arranging the electrons in the order of this, right? First one sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py, which means that these two orbitals always have the similar energy, right? That is why it is returning in the equal sign. Then sigma 2pz, then pi star 2px, pi star 2py, again similar energy. The last one sigma star 2pz, right? Okay. This is very important while writing the molecular orbital electronic configuration of different molecules, right? Now, the second condition is that if it contains more than 14 electrons, what will happen? The order changes, right? The position of sigma 2pz is here in the case of first case, but here it is showing here, right? After sigma 2s, it is sigma 2pz. This will be the complete order of energy of various molecular orbitals for the molecules having electrons greater than 14 electrons. Electrons greater than 14 electrons. For example, in the case of oxygen, right? In the case of one oxygen, it is 8 electrons, right? So, for O2 molecule, it is 8 plus 8, 16 electrons. Similarly, for F2 molecule, one fluorine contains 9 electrons. For F2 molecule, it is 9 plus 9, 18, right? Clear? Okay, Anish. Okay, we have just started about the hybridization. We have discussed about the hybridization of the organic molecules like ethane, and acetylene. Then we will be starting with the molecular orbital theory, right? Just watch the recorded session. Okay, this will be the order of electronic configuration. To write the electronic configuration of the particular molecular orbitals, right? Now, while writing the molecular orbital electronic configuration, there is a important term you have to be finding, that is the bond order, right? Whenever we are discussing about the bond parameters, I have already discussed about the bond order, right? It will be the number of bonds formed between two atoms or molecules, right? Two atoms. So, that will be the bond order. According to molecular orbital theory, it is predicting the formula to calculate the bond order, and it is given as, it is the difference between half of the difference between NB minus NA, right? Difference between NB and NA. This NB stands for number of electrons in bonding molecular orbital. Number of electrons in BMO, which means bonding molecular orbital. Then NA stands for number of electrons in anti-bonding molecular orbital. ABMO, right? Clear? This will be the formula to calculate the bond order of different molecules. Now, by using this bond order, we can predict the stability of molecule, right? We can predict the stability of molecule. For example, if I say that NB is greater than NA, which means that the number of electrons in bonding molecular orbital is greater than that of the number of electrons in anti-bonding molecular orbital. Then what will be this value? Whether it is positive or negative. NB is greater than NA, which means that NB minus NA will be positive value, right? So we can say that the bond order will be positive. Otherwise, we can say that this molecule is more stable, right? This molecule is more stable. Now, the second condition, if Nb is less than Na. If Nb is less than Na, which means that the number of electrons in anti-bonding molecular orbital is greater than that of bonding molecular orbital. So we can say that the bonding orbital is equal to bond order is equal to negative, right? Value will be negative. Then if Nb is equal to Na, what will be the value of bond order? If Nb is equal to Na, that is number of electrons in bonding molecular orbital is equal to number of electrons in anti-bonding molecular orbital. What will be the value of bond order? Zero, right? Nb minus Na will be equal to 0, which means that bond order is equal to 0. So we can say that whenever the bond order is less than 0 or equal to 0, the molecule will not be exist. Molecule will not be exist, or we can say that if bond order is less than or equal to 0, there is no, it is unstable, right? There is no any existence, or otherwise we can say that it is unstable, the molecule is unstable. Clear? Yes, fine. Now the next application is that based on the molecular orbital theory, we can predict the magnetic behavior of molecule, right? Whenever the molecule contains at least one unpaired electron, at least one unpaired electron or singly occupied electrons, we can say that the complete molecule is paramagnetic, which means that whenever a magnetic field is present in here, it is attracted by the magnetic field, right? It is attracted by the magnetic field. Then just opposed to that, we can say that if molecule is not containing any of the unpaired electrons, we can say that it is a diamagnetic molecule, or if it is a doubly occupied molecule, we can say that it is a diamagnetic molecule, which means that it is repelled by the magnetic field, right? It is repelled by the magnetic field. Clear? Okay, you will get a complete idea about these applications by taking the examples, right? Clear? Okay. First I am taking the hydrogen molecule, that is H2 molecule, right? Okay, H2 molecule. The first step you have to do that, writing the molecular orbital electronic configuration, right? Okay, H2 contains 2 electrons, right? For one hydrogen atom, it is containing 1 electron. For 2 hydrogen atom, it is containing 2 into 1, 2 electron. So, you have to write the electronic configuration. Okay, this will be the electronic configuration. According to the energy level, first orbital is filling sigma 1s, and it is important that in the case of all the molecular orbital, the complete occupancy is 2, which means that each orbital is completing by adding 2 electrons. Clear? Now, by writing the electronic configuration of H2, it will give it as sigma 1s2. Now, how to calculate the bond order? Half into Np minus Na, right? Nb means number of electrons in bonding orbital, it is 2. The number of electrons in anti-bonding orbital, it is 0 here, right? So, 2 minus 0 by 2 is equal to 1, which means that hydrogen is forming a single bond between the hydrogen atoms, right? Hydrogen molecule is forming a single bond between the 2 hydrogen atoms. Clear? Now, we can predict the magnetic behaviors also. Is there any unpaired electrons present? That is singly occupied electron. No, right? Because it is doubly occupied. So we can say that this H2 molecule is diamagnetic in behavior. Clear? Now, here is the second example, that is the He2 molecule, that is helium molecule. Hi Vidhu. Helium, right? Helium molecule. In the case of one helium atom, how many electrons are there? Two, right? So in the case of helium molecule, it is 2 into 2, 4 electron. So write down the electronic configuration. It will goes like this: sigma 1s2, then sigma star 1s2. Then what about the bond order? Taking the difference between number of bonding electrons and number of anti-bonding electrons. So we can say here 2 minus 2 divided by 2, that is equal to 0. What will be the stability here? Whether this molecule is existing or not. It is given that molecule is having bond order of 0. Okay, if we are taking the bond order, we can say that if the bond order is 0 or less than 0, it will not exist as a molecule. So we can say that He2 molecule is not existing, and because of bond order 0. Clear? There is a next case, that is the lithium molecule. First, find out the number of electrons. For one lithium atom, it is containing 3 electrons, right? So for 2 lithium atoms, it will form 2 into 3, 6 electrons. Now write down the electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, right? Sigma 1s2, sigma star 1s2, sigma 2s2. Find out the bond order, that is equal to half into how many number of electrons are present in bonding orbital here? Two plus 2, 4, right? Minus only 2 electrons present in the anti-bonding molecular orbital, which is in the sigma star 1s. So I am taking 4 minus 2. 4 minus 2, 2 by 2, that is equal to 1, which means there will be one bond is existing between 2 lithium atoms. Clear? That will represent the bond order of 1. Then what about the magnetic behavior? Whether it is diamagnetic or paramagnetic. Okay. Sigma star means it is the anti-bonding orbital of 1s orbital formed by the axial overlapping, right? Sigma means the axial overlapping of 1s orbital. Star represents the anti-bonding molecular orbital. Clear? Just go through the recorded session, then it will be more clear. Okay, whenever you are seeing any star in between the orbital, it represents that it is anti-bonding molecular orbital. Now, what about the carbon molecule? One carbon containing 6 electrons, right? So, in total, it will contain 12 electrons. So, writing the electronic configuration here, starting from sigma 1s2, then sigma star 1s2, sigma 2s2, sigma star 2s2. Then, what about the next order? Pi 2px2 and pi 2py, right? Which means that these two orbitals are in the same energy order. So, it will be forming, it will be filling electrons according to the same energy order, right? So, what about the bond order here? How many electrons are present in bonding molecular orbital? Eight, right? 8 minus This is one of the electron in the sigma star 1s. Then it is 2. 2 plus 2, 4, right? 8 minus 4, 4 by 2, that is equal to 2. Yes, 2, which means that bond order is equal to 2, which means 2 bonds are formed between carbon atoms. Clear? Then what about the magnetic behavior? Again, it is diamagnetic because there is no any unpaired electrons. Clear? Yes, right. Now the next molecule, it is nitrogen molecule, right? Nitrogen molecule is having 14 electrons. Okay, this will be the molecular orbital electronic configuration. Sigma 1s2, sigma star 1s2, sigma. Okay, this is sigma 2s2, right? This is sigma 2s2. Then sigma star 2s2, pi 2px2, pi 2py2, then pi 2pz2, right? In total, it will be 14 electrons. Then find out the bond order. Half into bond order is 3, right? Which means that in the case of N2 molecule, 3 bonds are formed between each nitrogen atom, resulting in the formation of N triple bond N, right? Then again, what about the magnetic behavior? Diamagnetic or paramagnetic? Diamagnetic, right? Because there is no any unpaired electrons, so we can say that this molecule is also diamagnetic in nature. Here is the next example, that is the oxygen molecule. Find out the number of electrons in oxygen molecule. How many electrons are present in the oxygen molecule? One oxygen contains 8 electrons. Then for oxygen molecule, 2 into 8, that is equal to 16 electrons. Then the point to be noted that for 16 electron, or if the molecule contains more than 14 electrons, there will be the order change, right? This will be the order change. Okay. After sigma star 2s, you will get the orbital of sigma 2pz. That is the main difference between previous case and this one. Clear? So starting from here, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2, then pi 2px and pi 2py have the same energy, so it will fill the electron accordingly. Then after that, pi star 2px, pi star 2py. Why there is no any 2 electrons each? Any idea? Okay. In the case of these particular orbitals, these are have the same energy, right? We already mentioned that the electrons are filling the molecular orbital according to the rule of Hund's rule of multiplicity and Pauli's exclusion principle, right? Here it is forming that after completing these orbital will be happening, right? Which means that whenever it is completely filled, then only it will go to the next one, pairing of the electrons happening according to Pauli's exclusion principle, right? So we can say that here the first electron is entered into the pi star 2px, then it is pi star 2py, right? Clear? Then what about the bond order here? Bond order. Two, right? Which means oxygen is forming O2 molecule by forming 2 bonds, or bond order is equal to 2. Then what about the magnetic behavior here? Whether it is paramagnetic or diamagnetic? paramagnetic, right? Because of the presence of these two unpaired electrons, we can say that the complete oxygen molecule is paramagnetic in nature. Whenever a magnetic field is present over there, it will attracted by the magnetic field. That is representing the paramagnetic behavior. Clear? Here is the next case, that is the O2 minus molecule, which means that 16 plus 1 electron, right? That is equal to total 17 electron. Write down the electronic configuration like this. The only change is that here 2 plus 2, 4, right? Okay, in total 17 electrons are present here. After completing the pi 2py orbital, it will go to the pi star 2px. 1, 1, right? In total it will be 16 electron. Then the next electron will enter into the pi star 2px in order to complete the doubly occupying, right? Clear? So it will form here 2, 1. Then therefore bond order is equal to while calculating the bond order, it will equal to 1.5 having the behavior of paramagnetic. Clear? Okay, these are the examples of different molecules having the electronic configuration, molecular orbital electronic configuration, as well as bond order and the number of unpaired electrons and the magnetic property. You can go through these examples, then just calculate the electronic configuration and checking whether it is having the same bond order or not, right? Now here is the practice questions for you. The first question is that according to the molecular orbital theory, find out the bond order of O2 minus CO and NO plus. What will be the answer? O2 minus CO and NO plus. First write down the molecular orbital electronic configuration, then you will get that bond order is equal to 1, right? 1. Then for carbon monoxide, just calculate the electronic, just write down the electronic configuration, then find out the bond order. Otherwise you must have an idea about the bond order of carbon monoxide, right? It is forming the triple bond, right? C triple bond O. So we can say that it is again 3, right? Then what about the speciality of these molecule? NO plus molecule. This CO molecule contains 14 electrons, right? 6 plus 8, 14 electrons. Again here it is also 7 plus 8 minus 1, again 14 electrons. Which means that these two species are isoelectronic in nature, which means it contains same number of electrons. As I already mentioned about the bond order concept, the isoelectronic species have the same bond order, right? So we can say that without calculating the bond order from the molecular orbital theory, we can say that the bond order of NO plus is equal to 3. Clear? Which means option A will be the correct answer. The same type of question, that is the difference between bond orders of CO and NO plus. CO and NO plus. This is the isoelectronic species, right? So CO have the bond order of 3. Similarly, NO plus have the bond order of 3. Then difference will be equal to 0. Therefore, option C will be the correct answer. Okay. This is the one more question. You can take it as a homework. One formula you have to be noted, that the magnetic moment is given as square root of n into n plus 2, where n is the number of unpaired electrons. First, calculating the electronic configuration, find out the number of unpaired electrons so that you can get the answer of this question. Clear? Okay, that's all about from my side for today. Okay, I hope you have covered the previous session we have discussed in the last class also. Today we have covered with the hybridization as well as the molecular orbital theory. And tomorrow we will be going to the last part of the same chapter, that is the hydrogen bonding. Okay, till then, bye bye all of you. Take care. Thank you so much.